In this lecture I am going to talk about temperature and heat. This is outline of this talk. First, I'll explain what is temperature, and then what is heat, the definition of specific heat. Then we talk about the calorimetry, and finally change of phase of the bodies. Let's talk about the temperature. What is the definition of temperature? Temperature is a measure of hotness or coldness of a body. But this definition is not so clear. To check that, let's imagine the following thought experiment. We have 3 beakers. The first beaker is filled with ice and water. The third beaker has filled with boiling water. Then the second beaker has a mixture of waters from beaker 1 and beaker 3. Now, then we are going to check its hotness or coldness of each water of each beaker. First we check in the first beaker by our fingers, and we feel that it's cold. Then if we check the hotness of the water in the second beaker, then we feel that it's warm comparing to the first beaker. And so this is thought experiment. Do not try to do this at home. This is boiling water. We are going to check the hotness of the boiling water, and if we check it with finger, we feel that it's very hot. After that, if we check the hotness of the second beaker again, we feel that now it's cold. We have 2 conclusions about the hotness or coldness of this water in the second beaker. In the first time we conclude that it's hot, it's warm. At the second time we conclude that it's cold comparing to the boiling water. So then this definition that the temperature is the measure of hotness or coldness is not so clear, because we have 2 conclusions about water in the second beaker. So the Scottish physicist William Thomson, which is Baron Kelvin or Lord Kelvin, he said that when you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot express it in numbers, your knowledge is of a meager and satisfactory kind. So that's why we need more precise definition of temperature, and we have to measure the temperature. How to measure the temperature, to express it in numbers. So to measure the temperature we use the thermometer. Thermometer is a tube made of glass, and inside it has some specific liquid. Usually it's mercury or alcohol. We have different kinds of thermometers. And in this thermometer usually we measure the temperature in degrees Celsius. So how to measure the temperature by using this kind of thermometer, and what is the principle, underlying physical principle in measuring of the temperature? So underlying physical principle is the dependence of the volume of liquids on temperature. So increasing the temperature, the volume of the body increases. Decreasing the temperature, volume of the body of the liquid decreases. So we can measure it. We can use this fact in thermometers. And in order to measure temperature by using thermometers, people first introduced the Celsius. Anders Celsius in 1742 introduces this measurement, and the basic was 2 points of water two temperatures of water. The first one is melting point of ice, or freezing temperature of water, is the same thing. He introduced it as 0 degrees Celsius. And for boiling water, so boiling point of water is 100. So he introduced this kind of scale and divided this interval into 100 parts, and each part is called degrees Celsius. So and equal distances between each temperature, and if you divide this in this kind, you can measure the room temperature is 20 degrees Celsius. So human body temperature is 36.6, it's about 37 degrees Celsius, etc. But in US, people use Fahrenheit scale, which is the scale of melting point of ice is 32 degrees Fahrenheit, and boiling point of water is 212 degrees Fahrenheit. Now, this is introduced by Gabriel Fahrenheit in 1714. And how to convert from Fahrenheit to Celsius and from Celsius to Fahrenheit, we will talk about a little bit later. And the third one of the unit of temperature is Kelvin, introduced by Lord Kelvin in 1848. This is based, we will talk about the Kelvin temperature a little bit later. So let's talk about relation between Fahrenheit and Celsius. So let's talk about the one temperature. So let's measure the temperature from 0 degrees Celsius, the freezing point of water. At this point, from this point we can measure the distance from 0 degrees to some temperature, for example some unknown temperature T. This is called H1, and the known temperature 100 degrees Celsius is H0. So same thing we can do for Fahrenheit. So we have to satisfy this relation. H1 divided by H0 in Celsius should be equal to H1 divided by H0 in Fahrenheit. And then by putting H1 is T minus 0, because H1 is between T and 0, and H0 is between 100 and 0 in degrees Celsius, and in Fahrenheit it's T minus 32, because it's 32 in Fahrenheit, and H0 is 212 minus 32. From this equation we can find T, and by simple arithmetic you can simple algebra you can find that T is 5 over 9 T in Fahrenheit minus 32 degrees Celsius. So let's check if 32 Fahrenheit, 32 minus 32 is 0. So 0 multiplied by 5 over 9 is 0. So this is 0 degrees Celsius. Or 212 minus 32 is 180, and divided by 9 it's 20, multiplied by 5 it's 100. So this is a formula to convert from Fahrenheit to degrees Celsius. And the similar, by using this formula you can find what is the relation, how to find Fahrenheit by knowing degrees Celsius. Same thing we can apply for Kelvin temperature. So what is Kelvin temperature? The meaning of the Kelvin temperature I'll explain in the next slides, but here you should assume that freezing point of the water is 273 Kelvin and boiling point of water is 373 Kelvin. You can see that it differs with degrees Celsius by 273. So 0 is 273, you add 273, 100 is 373 Kelvin. So you add 273. Or in order to find, if you know in Kelvin, you subtract 273 and you get the temperature in degrees Celsius. Okay, this is one example to conversion of from Celsius to Fahrenheit, and temperature of -5 degrees Celsius is equivalent to what Fahrenheit temperature. So it's given T in degrees Celsius, and you should find T in Fahrenheit by using this formula. You can find the solution of this example in your textbook. Now let's talk about the fundamental definition of temperature. So microscopic definition of temperature. Temperature, you know that every bodies, every materials, matter consists of small particles called atoms and molecules. For example, here you can see that the solid body or metal consists of the atoms in this very beautiful order, which is called crystals. So each atom, each point here is atom in the crystal, and it interacts with neighbor atoms. So in this picture, according to the molecular physics, atomic physics, each atom in the crystal, each ion, I can say, in crystal is not stationary. It oscillates, vibrates at the equilibrium position, and that's why it has an energy, kinetic energy, because of it has a mass. Each atom has a mass, and each atom has a vibration velocity, and it has kinetic energy. Kinetic energies of each atoms can be different, but in average, the mean value of average kinetic energy has the meaning of temperature. So if the temperature is high, then oscillation energy or motion energy of atoms are higher. Kinetic energy of atoms is higher. So if the temperature is small, then motion kinetic energy of the atoms is small, and that's why if we cool down the material, if we cool down the matter, its atoms moves very slowly with time during we cool it, and then its temperature decreases, and the smallest temperature possible in this process is when all atoms are becomes at rest. So all atoms stops its motion. This is the smallest possible temperature, and according to calculations, people found that this the smallest temperature is -273 degrees Celsius. So this is the smallest possible temperature. No, the smaller temperature than minus 273 degrees Celsius. That's why people introduced Kelvin units for that. So they took minus 273 as 0, and they call it 0 degrees Kelvin, 0 Kelvin, and then each change of each degrees Celsius is equal to each Kelvin. So delta T in Kelvin and in degrees Celsius is the same. So temperature of a body is a measure of the mean or average kinetic energy of the vibrating molecules or atoms of the body. Let's talk about the heat. What is the definition of heat? The sum of the potential energy and kinetic energy of all these molecules is called the internal energy of the body. So atoms or molecules have not only kinetic energy but potential energy also, because they interact with each other. That's why it has internal energy, which is the sum of potential and kinetic energies of all molecules or atoms. What is heat then? Heat is the amount of energy flowing from a body at higher temperature to a body at a lower temperature. Imagine you have two bodies, one is hotter and other is colder. Then if you make them in contact, then energy flows from a hotter body to the colder body. This amount of energy flowing from body at higher temperature to the body at lower temperature is called heat. The measure of the heat is joule. So this joule was introduced by James Joule. What is joule? So joule is amount of energy. So first James Joule performed an experiment showing that the heat has a meaning of energy. So we will talk about the experiment of the Joule later. But according to his experiment, he defined what is calorie. So calorie is defined as the quantity of heat required to raise the temperature of 1 kilogram of water to 1 degree Celsius. So imagine that you have 1 kilogram of water and you are going to increase its temperature to 1 degree Celsius. To do that, you need 1 kilocalorie of energy. And if you convert 1 kilocalorie to joules, 1 kilocalorie is 1,000 calorie, and which is equal to 4,186 joules. In physics, we also have British thermal unit of heat, BTU. 1 BTU is 1055 joules. Now let's talk about the specific heat. What is specific heat? So different bodies absorb a different quantity of thermal energy, even when subjected to the same temperature. Imagine the following experiment. We have 4 balls made of aluminium, iron, brass and lead, and all of them submerged to the liquid with some temperature, so we can measure its temperature. So all of them are in the same water, that's why all of them has the same temperature. All of them has the same size. And then if we put them at top of the paraffin, and Paraffin is, you know that it's candle, and due to they are very hot because uh, their temperature increases to very high temperature, and then paraffin starts to melt under the balls, and then they start to fall down. But in this experiment, people found Tyndall found that aluminium goes faster than iron second, and brass third, and finally lead is fourth. What does this mean? The aluminium has higher temperature exchange with paraffin. Iron is the second, brass is the third, and lead is fourth. That means depending on material, each material has different so-called thermal conductance or thermal conductivity. So temperature can flow from one body to another body, from the ball to the paraffin, depending on the specific heat. So the specific heat of a body is defined as the amount of thermal energy required to raise the temperature of a unit mass of the material to 1 degree Celsius. To understand what is specific heat, you can see this formula. So Q is heat, which is measured in joules or in BTU or in calories, kilocalories. It depends on mass, the specific heat, and change in temperature. And specific heat is Q divided by MT. M is mass, delta T is change in temperature. That means for aluminium, specific heat is 0.215 kilocalorie per kilogram degrees Celsius. That means that, you need 0.215 kilocalorie amount of energy in order to increase the temperature of aluminium, 1 kilogram of aluminium, to 1 degree Celsius. Same thing you can say about iron, brass, and lead. You can compare. The aluminium has highest specific heat. That's why it has smallest conductance, thermal conductance. That's why it falls last. If you see, aluminium has more specific heat, then it has more energy, thermal energy. That's why it falls first. Iron is the second, brass is the third, and lead is the last. So aluminium has more heat energy according to this formula, because C is higher, Q is higher. So aluminium has higher energy, thermal energy, which is heat. And lead has the smallest thermal energy. That's why lead is last and aluminium is the first. You can see the specific heats of most of the materials in this table. They are given in kilocalorie per kilogram per degree Celsius and in joules per kilogram per degree Celsius. If you compare, if you see from this table, the highest one is the water is 4186 joules per kilogram per degree Celsius. And the same material in ice is the same as water, but different specific heat, 2093, almost 2 times smaller. And you can see that metals has a smaller specific heats. Gold is 129, iron is 129, lead 129, platinum 134. They have smaller specific heats. Why? Because they have higher thermal conductivity. So if you touch at winter, if you touch metals, you feel that they are colder than the wood, for example, because wood has higher specific heat. So I said that water has the highest specific heat. That's why large bodies of water such as lakes, oceans tend to moderate fluctuations of the air temperature nearby, because bodies of water can absorb or release large quantities of thermal energy due to its higher specific heat. That's why undergoing only very small change in temperature. The example of this is weather in England. You know that the weather in England is not so cold because of surrounding water, but in the same altitude, in the same latitude, I mean in the same parallel of the Earth, for example, in Siberia, the weather is very cold comparing to England. That is because of Gulf Stream in the Atlantic Ocean. Gulf Stream carries the hot water from south, from Africa to Europe, to England. Now we talk about the calorimetry. Calorimetry is defined as a measurement of heat. These measurements are performed in a device called a calorimeter. This is calorimeter. This device consists of two glass cylinders and vacuum between them. And inside the calorimeter we can fill with the water, and it has the thermometer. We can measure its temperature of the water inside the calorimeter. And this device is used to measure the specific heat of unknown body. For example, if you have some metal and you want to measure its specific heat, you can put it inside this water and fix the change in temperature of the water by knowing mass and by knowing the temperatures. We can calculate the specific heat. So I will show it in the next slide. So basic principle underlying the calorimeter is the conservation of energy. So thermal energy lost by those bodies that lose thermal energy is equal to the thermal energy gained by those bodies that gain thermal energy. So thermal energy lost is equal to thermal energy gained. For example, if you put some body inside this liquid, then this body exchanges with temperature with water if they have different temperatures. And this equation is called heat balance equation. So thermal energy lost is equal to thermal energy gained. And how to calculate the thermal energy or the heat lost or heat released or gained. So you can do that by using this formula. So ms is the mass of the sample, mw is the mass of the water, mc is the mass of the calorimeter. And according to this heat balance equation, thermal energy lost, so the heat of the unknown sample Qs, so this is heat lost, equal to heat gained by water plus heat gained by calorimeter. And each Q in this equation can be written as mass of each substance multiplied by specific heat of each substance multiplied by thermal temperature change of each substance. Here, if we write this equation, and we can find from this equation what is specific heat of unknown sample. So by measuring temperatures of the initial temperature, final temperature of the water, and mass of water, mass of the calorimeter, and mass of the substance, we can, by using this formula, we can find the specific heat of unknown sample. Now we are going to talk about the last part of this lecture, which is change of phase. Change of phase means that we have three main different phases of matter. They are liquid, solid, and gas. So these phases and they can change. For example, if you imagine water, we can freeze water. Water is liquid, we can make it solid. Now it becomes ice. Or we can vaporize water, we can boil the water, and it changes its phase from liquid to gas. So the first one, fusion, is called fusion. It's change of phase from liquid to solid. The second one is melting, from solid to liquid. And the third is vaporization, from liquid to gas. And fourth is condensation, from gas to liquid. 5 is sublimation, solid to gas. And the last one of phase transition is called the change of a solid from one crystalline form to another. So example of fusion is, as I said, liquid to solid is freezing of the water. When you freeze the water at 0 degrees Celsius, it becomes ice. The melting is, you can melt the ice, for example, by heating the ice. It becomes liquid, it becomes water. Vaporization is liquid to gas. When you boil the water, you get gas, so vapor of water. Condensation is the water can be, the gas can be changed to, by cooling the gas, you can change it to a liquid. This is called condensation. And sublimation is solid to gas. Example of sublimation is when you vapor the solid itself. Solid itself can be vaporized. For example, the smell of the bodies is also vapor of this body. And change of solid from one crystalline to another crystalline. So crystal structure of the body can be changed. For example, crystal structure of snow and crystal structure of ice are different. But both of them are solid phase of water. So this diagram here shows the change of phase of the water. So imagine this experiment. We have a container inside, with ice inside, and we can measure the temperature of the ice, and we can make a fire, burn it. We can increase the temperature of this ice, and look at how temperature changes with time, and by measuring with thermometer and plot it on this diagram. So initially the temperature was minus 20 degrees Celsius. This was initial temperature of the ice. Then by heating, its temperature increases with time up to 0 degrees Celsius when the ice starts to melt. In this part it's ice, and during its melting its temperature doesn't change. This is very interesting experiment, very interesting observation, because why its temperature doesn't change? Because all the heat given by the fire is converted to change the phase of the ice to liquid, to water. That's why temperature doesn't increase. After all of the ice can change it to water, then again temperature starts to increase, and now all the ice is changed to its phase to the liquid, to the water. Now its temperature becomes increasing up to 100 degrees Celsius. Again, in the 100 degrees Celsius, its temperature again is constant until all the liquid, all the water vaporizes. So all the water should be vaporized. That's why temperature doesn't increase. And after all of the water converted to the vapor, now its temperature again increases. You can see these two parts in this diagram. So we will talk about these two parts. So amount of heat in this part, we can talk about this change of phase. The latent heat of fusion. What is latent heat of fusion? Is the amount of heat necessary to convert 1 kilogram of the solid to 1 kilogram of the liquid. The total heat of fusion is QF is equal to M LF. This is latent heat of fusion. So for example, for water, is latent heat of fusion is 80 kilocalorie per kilogram, or 3.34 10 to the 5 joules per kilogram. That means in order to increase, in order to convert 1 kilogram of 1 kilogram of ice to 1 kilogram of water, you need 80 kilocalorie of energy, or 3.34 10 to the 5 joules of energy. Imagine that you have 1 kilogram of ice at 0 degrees Celsius, and in order to make it 1 kilogram water at 0 degrees Celsius, you need 80 kilocalorie amount of energy. And the same thing we can say about latent heat of vaporization, LV. Latent heat of vaporization is QV divided by M, or QV is mLV. So QV is heat of vaporization, LV is latent heat of vaporization, M is mass. So what does this mean? This formula means that, for example, water latent heat of vaporization is 540 kilocalories per kilogram. That means if you have 1 kilogram of water at 100 degrees Celsius, in order to change its phase to gas, in order to obtain 1 kilogram of vapor, you need 540 kilocalorie of energy, or 2.26 million joules per each kilogram of water. You can compare the latent heat of fusion and latent heat of vaporization, and you can see that latent heat of vaporization is much higher than latent heat of fusion. You can see it in this diagram. So here time needed to going from solid to liquid is much smaller than time needed to make liquid to the gas, because here you need latent heat of vaporization and here you need latent heat of fusion, and latent heat of fusion is much smaller than latent heat of vaporization. Next example is about converting ice to steam. So compute the thermal energy that is necessary to convert 5 kg of ice at minus 20 degrees Celsius to superheated steam of 120 degrees Celsius. So in order to solve this problem, you have to use the total energy, total heat necessary to do that is the sum of thermal energy needed to heat the ice up to 0 degrees Celsius, then plus thermal energy needed to melt the ice, the fusion heat, plus the energy needed to heat the water to 100 degrees Celsius, plus the energy needed to boil the water, so this is heat of vaporization, plus the energy needed to heat the steam to 100 degrees Celsius. For each of these Q, you can use formulas given here for fusion, for vaporization, and for change in temperature. You can use this formula. So here is second example about mixing ice and water. If 10 gram of ice at 0 degrees Celsius are mixed with 50 grams of water at 80 degrees Celsius, what is final temperature of the mixture? The thermal energy gained equal to thermal energy loss. This is heat balance equation. And Q fusion plus Q ice to water is equal to Q of water. And if you write the Q of fusion is M latent heat of fusion plus Q is mc delta T is equal to mc delta T. So from this formula we can find final temperature of the mixture. So final temperature of the mixture is mass of the water, specific heat of water, initial temperature of water, minus mass of the ice, and latent heat of fusion divided by mass of icy water, specific heat of water, and mass of water, specific heat of water. We can get 53.3 degrees Celsius. This is our lecture for today. Thank you for your attention.